Hey everyone, today we are going to talk about Graham's Law of Effusion. And what that means is effusion is when gas particles escaping through a tiny pinhole in a container. So, for example, if I have a container, and let's say I have this tiny pinhole, you guys can see how it's not connected, right? The container's not connected right here. And I have some gas particles moving around, okay? And effusion is, so these guys move in totally random directions, right? Straight line, random directions. We learned that from kinetic molecular theory on Monday. So let's say one of these gas particles just escapes through this hole here. It's like the screensaver scene in The Office when finally it hits the corner. So this is like one of the gas particles finally gets out of this pinhole. Okay. Now we're going to talk about different rates of effusion. So obviously, if you know what the word rate means, you would know that the rate of effusion would be the speed at which a gas effuses. Okay, so typically this will be some sort of molar concentration, or I'm sorry, moles. Typical units would be moles per second. Okay, how many moles of gas escape per second? Right. Now, if we go back to kinetic molecular theory, and one thing you need to know is that the rate of effusion depends on the speed of the gas particles. Okay, so we'll just pretend we're just taking the average speed. The different gas particles are going to be moving at different speeds at all times, but the fact of the matter is that smaller gas particles move faster at a given temperature. So let's think about this. We know from kinetic molecular theory, I'm going to just call it KMT, tells us that the average kinetic energy depends solely on the temperature, right? Okay, so at a constant temperature, two samples of gas will have the same kinetic energy, right? So let's say I have two samples of gas. I'm just going to draw out another container that has two samples of gas in it. So boom, 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 boom. I have two samples of gas. So one of them I'm going to make red gas. And the other one I'm going to make green. Okay. So the kinetic energy, so let's say we're at 35 degrees Celsius, okay? The kinetic energy of gas number 1 is equal to the kinetic energy of gas number 2 because they're at the same temperature. Okay, so as long as two samples of gas, no matter how different they are in mass, as long as they are at the same temperature, they have the same kinetic energy. So what does that tell us about the speed of the gas particles at a given temperature? Let's think about this, right? So if I have 1/2 the mass of the first, and mass, when we talk about mass, we're talking about molar mass here. The mass of the first gas particle times the velocity of the first gas particle squared equals 1/2 the mass of the second type of gas particle times the velocity of the second type of gas particle squared. So now we can see, if we think about this, if the molar mass of 1 is greater than the molar mass of 2, then what do we know about their velocities? If their kinetic energies are equal and the mass of 1 is greater than the mass of 2, then the velocity of 2 has to be greater than the velocity of 1. And we said the rate of effusion depends on the speed of the gas particles. If the particles are moving faster, then there's a higher likelihood that they're going to get to that pinhole and escape that pinhole. Okay? So now what we can do is we can talk about the ratio of the molar mass to the rate of effusion. So the velocity is completely proportional to the rate of effusion. So what we can do is we can derive an equation here. So what I'm going to do is I'm just going to cross out these 1/2s here. Cross it out. So I know that the mass of the first gas particle sample times the velocity squared is equal to the molar mass of the second one times the velocity of the second one squared. So then I'm just going to rearrange this equation to put the masses and the velocities on the same side. So then I can say that the mass of the first sample over the mass of the second sample is equal to the velocity of the first sample squared. The velocity of the second sample squared over the velocity of the first sample squared. What I did here is I multiplied both sides by 1 over m2. And then I multiplied both sides by 1 over v1. Okay, so squared. So then, to simplify this equation, I can then say the square root. So then the square root of v2 over v1 is equal to, these are squared, so v2 over v1 is equal to the square root of m1 over m2. And so this, we're going to write as v, we said is it is directly proportional to the rates. So we're going to say rate 2 over rate 1 is equal to, and we said the m is the molar mass, is equal to the square root of the molar mass of 1 over the molar mass of 2. Okay, so That is Graham's Law of Effusion. I do want to do one practice problem with you guys as well, quickly. So let's say that a sample of oxygen gas effuses at a rate of 0.34 moles per second, and a sample then we're going to say, what is the rate of effusion of carbon dioxide gas at the same temperature and pressure? Okay. Okay. So here what we're going to do is we're going to say, okay, my rate, I'm going to call oxygen 1. So rate of O2 is equal to 0.34 moles per second. And then I'm going to say the rate of carbon dioxide, CO2, equals question mark. Okay, I know that the molar mass of O2 is 16 times 2, which is 32 grams per mole. And then the molar mass of CO2 is equal to 12.01 plus 16 times 2, which is 44.01 grams per mole. Remember, I always want you to go to the hundredths place with molar masses. So now what I'm going to do is I'm going to plug these in. I'm going to say rate of O2 over rate of CO2 is equal to the square root of the molar mass of CO2. Remember, they are diagonal from each other. So rate of O2 over rate CO2 is equal to the molar mass of CO2 over the molar mass of O2. Okay, so then I'm just going to go 0.34 moles per second over the rate of CO2 is equal to the square root of 44.01 divided by 32. Okay, so then I'm going to get 0.34 divided by rate of CO2 is equal to the square root of, hold on. Okay, so 44.01 divided by 32 is 1.375, and then we're going to take the square root of that, and that's 1.17. Okay, we're going to do a little switcheroony here, boop-a-doo, and we're going to get 0.34 divided by 1.17 equals 0.290 moles per second, and then is equal to the rate of CO2. So that's it for today. That's Graham's Law of Effusion. One other thing that will help you out a little, actually, is the time it takes sample number 1 to effuse over the time it takes sample number 2 to effuse is also equal to these things. But notice that it's 1 over 2. And so these actually correspond to the molar masses. Okay, they actually correspond to the molar masses, because if this one has a lighter molar mass, then this one, then it will effuse faster. Okay, so that actually makes sense. And then this one, if it, so if this is, if this one is lighter, then the time it takes is going to be inverse to its actual rate, right? So have a wonderful rest of your day.